Okay, hello everyone and welcome back to the Bangalore Theory Seminar Series. Today we have with us as a speaker Karthik CS. Karthik is an assistant professor at Rutgers University. He did his PhD from Weizmann Institute of Science and then he held postdoc positions at Tel Aviv and New York University. His interests lie in complexity theory and discrete geometry with an emphasis on hardness of approximation, fine-grained and parameterized complexity. Today, he'll be talking about constant rate isometric embedding of Hamming metric into edit metric. So let's welcome Karthik.
Thanks. Is this on? Right. Okay, sounds good. Yeah, so today I'm going to talk about something with a lot of co-authors. This work started as something in Dymax, and then I was visiting with my student Insight, and it carried on. The slides are due to PhD student advised by me, Mursaleen. 99% of what you'll see is from him. My main contribution is to change his name from the title and put my name there. So all the pictures are from him. Okay, so let's start with the two distances of interest. One is Hamming metric. So let's say you have two strings. Let's assume they are binary. The Hamming distance is the number of character substitution required to transform the first string to the second string. So here, for instance, you would change the 0 to 1, then you keep the 0 as it is, then you change that to 1, then you change it to 0, and to 1, and to 0. So there are 5 changes we made. So the Hamming distance is 5. The edit distance, we are allowed to not only substitute, but also delete something and insert something. So we can delete any character and insert any character. So the same pair of strings, what we can do is identify the first entry, delete it, and then insert it back at the very end. And then change the first one to 1. So we made 1 deletion, 1 insertion, 1 substitution. So the edit distance is 3. So as you can see, the Hamming distance is an upper bound on the edit distance, but they can be quite far apart. To see this, for instance, consider the vector 0, 1, 0, 1, 0, 1, 0, 1, 1, 0, 1, 0, 1, 0. Their Hamming, if you have n bits, their Hamming distance is n, whereas their edit is 2. We are interested in isometric embeddings. For this talk, we will focus on just 0, 1 isometric embeddings over 0, 1, but we have results on larger alphabets as well. So an isometric embedding is basically you take the 2 to the n points and you embed it in some higher dimensional space, but equipped with the edit metric. So you want that for every pair of points in the original space, after the embedding, their distances remain exactly the same in the new metric space. So I'm not allowing, for instance, a constant factor there, explicit constant. Those are called one embeddings. So let's just look at isometric embeddings where the distances are preserved even with the scalar being 1. Okay. And the rate is basically how much did you have to blow up. So it's not even a priori clear it's possible, but if it is possible, then we want the smallest blow up. And the rate captures that. It's the original dimension by the new dimension. Yes.
The mapping requires the inverter.
Yeah, let's say it's supposed to be. Depends on whatever the applications are. But in our case, it is. Okay. So one would actually say that the more natural direction is to embed the edit metric to the Hamming metric. And the reason is you're embedding a hard metric into an easy metric. So if you had algorithms in the Hamming metric, then which is an easier metric to develop algorithms, it would imply something for the edit metric. But we are doing the reverse because I don't do algorithms. And that means that whatever hardness we have in the Hamming metric, if we had an isometric embedding, then it also implies the same hardness for the edit metric. Just to give you an example, think of this red-blue closest pair problem. You have a bunch of red points and blue points in 0, 1 to the d. And we can, assuming some fine-grained complexity assumptions, you can show that the best thing you can do is to sort of check every possible pair, every possible red-blue pair. And so you can claim that in the Hamming metric, there is no n to the 1.99 time algorithm for endpoints. And suppose we had this isometric embedding from Hamming metric to edit metric. So we just use this embedding and we get these new strings, but the distances are preserved exactly. So the closest pair before will remain the closest pair now. So we can conclude there is no 1.99 time algorithm for closest pair now in the edit metric. This has applications in pattern matching and computational biology, genome sequencing.
Depend on capital N or small n? Like,
I haven't talked of the rate yet. So the rate will come in how much. So where is the role of rate? So it's captured here. If you had a rate R embedding and you're embedding from Hamming to edit metric, and if you know, so this is like a meta theorem. If you know a problem is hard in d-dimensional Hamming, then it's hard in d over r dimensional edit. So rate is the number between 0 and 1, so you get a blow up. So this is an approach, it's actually well studied, and the best before our work was like 1 over log d was the rate. I'm going to give you an intuitive explanation later why this 1 over log d comes up. And as you can guess from the title, we can get a constant. So what does this in particular mean? We know that there is no algorithm running in time n to the 1.99, assuming some assumptions like set, which can compute the closest red-blue pair when the dimension is order log n. And we know that there's an isometric embedding which blows up by a factor log d, which will be log n. So you get that there is no 1.99 time algorithm for the closest pair problem in the edit metric when the dimension is log n times log n. And this is very frustrating because edit metrics are harder. So the fact that we have a worse dependency in the dimension makes no sense. You want to get log n. In fact, you want to get something less than log n, whatever. Like if it was 10 log n, you want to get 9 log n because edit metrics are harder to do things. But fine, at least let's get log n. But yeah, we don't know because of the 1 over log d. Okay. From now on, we'll just assume all embeddings are from Hamming metric to edit metric. Whenever I say an embedding, I mean that. So we have, does there exist a constant rate isometric embedding that will sort of, give all these applications? And then if there is, what is the smallest c? Like let's try to optimize the rate. This is of interest, even just combinatorially speaking. You have the distance matrix coming from the Hamming space. What is the smallest edit space where I can isomorphically embed it as a subgraph? Okay, so our first main result is that rate 1 over 8 is possible. So not only is a constant, it's actually like for it, you take n bits and replace it with 8n bits, and this gives you an isometric embedding. And this gives like a bunch of applications. That closest pair, discrete one center, you're given n points and you want to pick a representative point which minimizes the maximum distance. These are subquadratic hard in the edit metric with the tight dependency in dimension, which is log n. And clustering Steiner tree, again, we get log n dimensional hardness in edit metric. And they have been studied in the edit metric for a while now, since the 80s. So this gives good applications for us. So it sort of spreads across areas of the application. And we also have a negative result to the isometric embedding. And this is sort of surprising. We show that 15 over 32 is impossible. Half is a very intuitive number to have. So it's like every one input bit I have add another bit as part of my embedding. And so sort of half, it's easy to show that half is sort of easy to rule out if you have rate better than half. It means that I had n bits, and if somehow I have now 1.99 n bits, there were 2 input bits that are sort of together. And you can try to cheat somehow here. So half with some work is easy to rule out, but getting better than half is a bit non-trivial. I will go back to why this is more non-trivial later. But the proof itself tells us something very nice about isometric embeddings. It's like isometric embedding has nothing but saying all distances are preserved. But we will show later, at least I will hint at later, that the embedding must have a specific structure, which is what you think it is. It's like a padding structure. Otherwise, it's not an isometric embedding. Okay, so I'm going to focus now on the first result, but without a constant there. It's just some O of n, some large constant. It's 153. So let's see this proof. I'll try to show this proof as much as possible with full detail. To go back, we have edit distance. And in edit distance, we have what we can call as alignments. So you can see that if you can write the two strings down, and a green alignment is an edge where it matches on the both endpoints. So it's a 1 and a 1 or a 0 and a 0. A red edge is when you have to make a substitution. And if there is no edge incoming, it means either it's inserted or deleted. If it's at the top, it's deleted. If it's at the bottom, it's inserted. So we can have this notion. So edges with different endpoints are substitution, same endpoints are matches. Symbols without an edge are deletions in X and insertions in Y. And notice that the Hamming distance corresponds to the alignment being just vertical. And yeah, you just have red, everything has an edge, and it's either red or green. So let's make a simple proof that isometry is achievable if you have an unbounded alphabet size in the output. Okay. So what we'll do, so let's say we have these are two strings X and Y. I'll just introduce new characters, each time a new thing. And I have no incentive to align across. So because I have to just do everything vertically now. But I've blown up from the alphabet size being 2 to basically n plus 2. But the length itself, I've just added one thing. So n became 2n. The problem is, of course, the alphabet size is not binary. It's n. So we want to replace the string 2, 3, n plus 1 with a string comparable length over finite alphabet. That's the first starting point. And then you want to understand what exactly is this property we need. Okay, let me make my remark here. So you could think of just replacing 2 with log n bits, which is its binary representation, n with log n bits and so on. The problem is you can cheat somehow. Because it depends on which n you have, like in edit, they might align very well, 2 different binary representations. So there is a way to cheat in these things. So you don't want to do that. But if you take random order log n bits, so I don't know, 100 log n bits randomly for each character,
Screen.
Should be control alpha.
Control L.
Yeah.
Okay. Yeah, I think it's being recorded.
Okay, so we want some dissimilarity property, which I'm going to formalize now. Okay, so for some parameter alpha, we call a string W as alpha locally dissimilar. Is if you take any substring S and you try to align it with itself without allowing vertical alignments. Okay, so for instance, your S could be 1010, and you try to align it with itself. So you will map the two 10s down this way. So this is called the self-edit distance. So if I want to map to myself and I don't allow any direct vertical alignments like in the Hamming thing, then the point is it said alpha locally dissimilar if the cost of the edit distance of mapping to itself is at least alpha times its length for every substring S of W. This is like a property we want. The question is, when can we achieve this? On what alphabet and so on? Notice that the string 2, 3 up to n+1 is one locally dissimilar. If I take any substring and I try to align it to itself without allowing the vertical, I have no matches at all. So I just alpha equal to 1, I pay the whole thing. So in this really nice work, and this is proved using the Lowash local lemma, they showed that for every alpha between 0 and 1, there is an alpha locally dissimilar string, as long as the alphabet is 1 over 1 minus alpha whole square. So if we fix a constant alpha, this is a constant alphabet size. And I claim that if we have this, we are already enough to prove some constant rate. And that's the rest of the proof now I'll show. The theta holds some very large constants, and this will come into our rate later. We'll talk about it. Okay, so the point is it's there for every alpha, right? So let's fix alpha to be 1/3. So for 1/3, you have a string of length 3n, such that if I take any substring of this 3n length string, let's say S, the edit distance to itself is at least that length of that over 3. Okay. And then we take our input, which is x and y, and take this 3n length thing, chop it up into blocks of size 3, and just use that as the padding. We know that this 3n length thing is on some constant alphabet size. It's 1/3, so it's like 1 minus 1 over 1/3 the whole square. Okay, so we have this is our new embedding, and I claim this is isometric. So let me repeat the isometric embedding again. You take any string x, and you have some fixed 3n length string, which is 1/3 locally dissimilar on some large alphabet. And then we chop it up into blocks of size 3, and we just insert it between every 2 consecutive input bits. Okay. We have it on some large constant alphabet now. We'll then reduce it to binary later. Let me first show that this is isometric. In other words, yeah, the Hamming distance is the same as the edit distance for every pair, x and y. Okay, suppose it's not the case. So suppose that there is some 2 strings x and y, such that after the embedding, the edit distance is less than the Hamming. Okay, let's fix them, x and y. And now what I will do is I will partition the length of the string into intervals. So there is this vertical intervals where everything is a vertical match. And then there are things where there is no vertical match. So you can partition the length into these parts. So let's call that I1, I2, I3, I4, and so on. So we are interested in the nowhere vertical intervals. So it's like you have 2 consecutive intervals which are vertical here, and in between here, there's no vertical match at all. Okay. By an averaging argument, we know that there is some interval I of length n, such that its edit cost is less than the Hamming cost. Right? Because whenever it's doing a vertical, it's equal to the Hamming cost. If overall it's less than the Hamming cost, there must be a nowhere vertical interval whose cost is less. So in particular, the Hamming cost is L over 4. Because for every 1 bit, we added 3 bits of things. So Hamming cost, it would just match all the padded things as it is. So the Hamming cost can only come from the new input things, which is at most L over 4. And we know that the edit cost is less than L over 4. Okay? So our goal is, if the cost is less than L over 4, then something goes wrong with the local dissimilarity. And the idea is the following. So fix this interval. There is no vertical alignment. Remove the input symbols. So remove the 0 and 1s. So you're left with these 2 strings, S and S. Okay. And we know that its length is 3L over 4 because you removed 1/4 of the input bits. And this is supposed to be coming from a locally dissimilar string. So first see that the edit cost of S and S is at most the edit cost in I. I mean, because I've just removed things. So it's an upper bound, the edit cost in I. So we know that the edit cost between S and S is at most L over 4, which if you write it in terms of the length of these things, L prime, which is 3L over 4, it's L prime over 3. So you found a substring whose edit distance to itself is less than L prime over 3, which is contradicting the 1/3 locally dissimilar property. So that's it. That's a contradiction. Okay. We have an isometric embedding to some constant. So input is 2 bits. I mean 2 alphabet size of 2, and the output is some large constant alphabet, but it's an isometric embedding. And if you want to make it to 0, 1, all you do is you take this large alphabet, you represent it using its binary representation and pad it with equal number of zeros and equal number of ones. So you don't allow any alignment at all. So you have basically 0, A, B, C, 1, and now your A is basically 0, 1, 0, B is 0, 0, 1, C is say 1, 0, 1, and then you have 0 to the K. Like K is the number of the size of the alphabet, in bit representation. And we can show that this remains an isometric embedding. Okay. Sorry?
Why do we add?
Because you don't want these matches from the thing here to the input things. So you don't want any of those to sort of kill the isometry. You want it to stay vertical. And one way to do it is just have a bunch of zeros. So you have no incentive of going non-vertical. And ones, that's it. Okay. You can see that the rate depends on log sigma. Right? Okay, so this gives an isometric embedding, but the rate depends on log sigma. And as I told, log sigma is some constant times 1 minus 1 over alpha square. So it's log of whatever that hidden constant is. The hidden constant turns out in their work to be 4900 E squared, which is like 37,000 roughly. Even if you take log base 2, it's still a large number. Right? It's, I don't know, like 14. So you're already paying 1 over 14 just from that. And then on top of that, your choice of alpha. So if you put everything together with all the things we have with this 0 to the K, 1 to the K, you get a rate of 1 over 153. We want to bring it down to 1 over 8. Okay, so let's go back though. We have already done something. We have shown that there's an isometric embedding from n bits to 153 n bits, which was not known before. And this gives you tight applications. The dependency in dimension is tight. It's order log n. So how do we get rate 1 over 8? Well, we introduce a new notion of binary error correcting codes in the arithmetic with some very robust distance guarantees. Okay. And we call it misaligners. And it's robust in 2 senses. In the first sense that the string itself is not just over 0, 1, but 0, 1 and while characters. So 0, 1 star. And it has distance guarantees even with the star taking 0 or 1. And second, it has distance guarantees. It's not just the distance between two code words, but you can concatenate two code words, look at substrings, and it still guarantees some distance. So I'm going to formalize what this is. So we have misalignor with 4 parameters, m, k, t, and alpha. Okay. K is the number of strings in our misalignor. So it's the number of code words. M is the length of the code word. M is the length of the code word. K is the number of code words. Each code word itself looks like this. It's like a block of size t, where you have first a while character and then a bunch of binary things, t-1 binary bits, and then again a while character and then t-1 things. So t is the length of this block. And finally, alpha is some relative distance, which I'm going to tell what it is. So there are 4 parameters: the number, the length, the block size, and the distance. Okay. So what do we want from this? It's like if you take any length of, you take any 3 of them and stick them together, then you can show that the best, it preserves isometry. So the best thing you can do is vertically align. So locally, when you just look at any 3 of them and stick them together, you don't have to worry about things not being isometric. So if you do anything other than vertical alignment, you just pay more in terms of edit distance. That's the first guarantee we want. The second one is if you take any 3 of them and you stitch them together and you take one of them on top and you look at its, you can take a bit of that code word, a bit of this code word, like you can spread it out, you still don't gain anything in terms of edit distance. Right? So the distance is at least alpha, even if you do all these. And you can extend it. I can take a bit of, you can take any 3 and any 3. I can take a bit here and a bit here, and you really don't gain anything. It's alpha times the length that you're taking, basically. So these are the distance guarantees we want. It's a lot of guarantees. And we'll see how we get all of these guarantees. And so that's our first ingredient, which are called misaligners. Our second ingredient is something we already saw before, but with a slight twist, called epsilon locally self-matching strings. So this is just for some parameter epsilon. W is said to be epsilon self-matching. Is if you take any substring and you look at the longest common subsequence with itself, where you don't allow substitutions, then you then also there's no vertical edges. So there's no substitutions of this kind, of the Hamming kind, or of the aligned kind as well. So it has to be just insertion and deletions. Then for any substring with itself, the longest common subsequence length is at most epsilon times the length of that string. So it's, if you just align shift it by a bit, then it just looks very different. That's what it's guaranteeing to you. Okay, so with these 2 ingredients, we can show the embedding. And as a remark, if you look at the 1, 2, 3 end string, it's 0 self-matching. So you can't match to itself at all if you don't allow vertically. Okay, so our embedding is as follows. So you have some input X. First, we start with this locally self-matching string, which is given. It's like a fixed thing given to us. It's even think of it as an infinite thing. But it's over some large alphabet, okay, large constant alphabet W. So it's say 4, 1, K, whatever. Okay. Now, but it's on some large alphabet. So we take a misaligner with the number of code words equal to the alphabet size. And we replace each alphabet in W, like each letter in W, with one of the misaligner code words. So let's say 4 is replaced with the 4th code word, 1 is replaced with the 1st code word, K is replaced with the kth code word, and so on. And when we do this, we have 0, 1s, and then stars, while characters. Okay. There's a while character at every T positions. And now we take the input and then put them in the while character places. So you had initially n bits. Now you will have Tn bits. So the rate is 1 over T. So that's fixed. So we have a rate of 1 over T, where T is a property coming from the misaligner. So the block size. Okay, good. And we need the misaligner size to be at least the alphabet size, so that we have a unique code word for each alphabet, each character in the alphabet. Okay. So it's isometric, but is it isometric? The answer is yes. It requires more work, but yes. In fact, we can show the following, that if you had a misaligner with M, K, T, and alpha, as long as your T is, you can just look at the expression on there. 1 over 1 minus epsilon times alpha. What do we want? We want alpha to be as large as possible and epsilon to be as small as possible. So you want the locally self-matching thing to be the epsilon with very small epsilon, and alpha, which is the distance, to be as large within the misaligner. So it's a parameter of the two things that we care about, the misaligner and the locally self thing. The epsilon self-matching. Yeah, if you take S and yourself and you try to align but not vertically, you only have an epsilon match. I think it's instructive to think of the locally self-matching thing as a global property and the misaligner as some local property. And we combine the two things. Okay, suppose otherwise. So let's assume it's not an isometry. Then you have some interval I where the Hamming cost exceeds the edit cost, like before. And the Hamming cost is at most I over T, right? Because you can always just map the padded strings to itself. So only from the input things, which is every T locations you get one, you pay Hamming. And then you want to show that if T is large enough, which is whatever we just saw now, then edit cost is at least I over T. So it's an isometric embedding. And the idea is just the same. Look at this specific interval. It has some alignments which are not vertical. And you assume just for the sake of simplicity, there are no partial blocks at the end. So you've cut in each nice block. Now we can classify all the top blocks. Okay, so let's say all the blocks, each block is of size T, right? Like so a block is completely matched to something below. So you have, say, B0 or whatever. Is there a good block here? I can't see it in the picture, but so you have a block on top, which is matched to a block at the bottom, but it's not vertical. So it's aligned, but it's exactly completely matched. So we call those blocks bad. Intuitively, it's like you had a locally self-dissimilar string and you wrote K here and K somewhere here, and these two you expanded into those code words and they completely match. You have block Bi, which is overworked. If it's spread downwards, is more than 1 plus alpha times its own length. So it's going down and spreading a lot. And then the rest are all good because we can handle them. So what do? If it's a bad block, then of course its edit distance is 0 because it's matching completely. But the epsilon self-dissimilarity property guarantees only an epsilon fraction of the time this happens. So, okay, fine. This epsilon fraction of the times, I don't care what happens. And the remaining 1 minus epsilon fraction of the times, if you have an overworked block, its length as at the top is m, but at the bottom is 1 plus alpha times m. So there is alpha m insertions at least. So I've at least gained alpha m as the cost. And in the good block, if it's going from m to something small, then the misaligner property tells the distance has to be at least alpha m. So in either case, I'm gaining alpha m on 1 minus epsilon fraction of the blocks. So that's how we get this distance. And if you just choose your T to be now greater than the denominator, like those two things, we have that the edit cost is more than I over T. Okay. Yes. The bad blocks is when you have a B1 and assume B2 is the same, B2 prime is the same as B1. Right? They're both basically they were just one character in a new alphabet, right? And then you replace them with these code words. What if those two were the same? Then I have a non-vertical thing that matches. And now they're replaced and their edit cost, they're exactly the same block. No, we are, right? It can just be there's no edge. If there's no edge at the top, it's deleted. Yes. So the way you can think of it is when you have a green edge, you don't pay. So the amount you pay is m minus the green edge. At the top, it's deletion and bottom, it's insertion. Any more questions? It's not bad. Should be fine. So the proof takeaway is that misaligners ensure that nothing bad happens locally because of this property that they have. So everything small, it handles it. And the self-matching string is like a global property that if you take any large enough thing, epsilon fraction fails, but for the rest, you can guarantee they are dissimilar. So fine, there are a small number of spurious matches, but that's fine. We can handle, we just accommodate them. So this local goodness, which is guaranteed by the misaligner, is sort of spread globally. Okay, so there are now I have to tell the construction of these misaligners and self-matching strings. So we know that there is a misaligner with these parameters. That is, it's of length 320. There are 676 of them. The block size is 8. So that means 1 wild character and then 7 bits. And the distance between whatever the robust distance guarantees we wanted with alpha equals 0.1625. And how do we know this? We wrote a code and then we run it, let it run for 3 months, and it outputs these things. In fact, this is the, if you want to try to build it by hand, there's no real hope because there is no, these are very weird objects. So there is no pattern or anything to figure them out. They just find them brute force. In this akin to coding theory, right? Like you, when you do code concatenation, you have a global code, which is very nice, like read Solomon or whatever. And then you have a local code, which is very short, and that you just do by brute force. It's guaranteed. Okay. So in order to obtain isometric embedding, we want the epsilon parameter to be like 0.224. Okay. And you want an alphabet of size 676. That's what we get from these things. We set your alpha, you set your t, and you get an epsilon. And so you want an alphabet to be 676. So you want an epsilon with that value. So now the question is, does there exist this infinite string over alphabet 676? So we need to work, a bit is a bit exaggerated, like it's really a lot more. Because if you just use the known things in literature, all these synchronization strings and so on, you get 722,000, and we want 676. So you have to really improve this Lowash local lemma analysis like by a lot. And we do. So this e square over epsilon square is inevitable. And what's the constant next to that? So we can make it arbitrarily go close to 1. So we show that there is an epsilon locally self-matching string of size e square over epsilon square. Remember, after that, the constant was 4900. And now we can make it something arbitrarily going to 1. And with this, we are good because now we can show that there exists 0.224 locally self-matching strings over alphabet of 553, which is fine. We wanted it over 600 something, so this is fine. But yeah, this required a lot of work. Oh, how do we prove this? So no, you look at the LLL analysis, and then yeah, and then you use the constructive LLL to show it. Yeah, the point is it was always LLL, but when you try to analyze it, you get all these analytic expressions, and you just try to upper bound all these things.
Even the previous one was this kind of LLL.
Yeah, okay. These objects locally self-matching, the only known proofs is through LLL. There are like several papers, all of them, because they're not supposed to exist. A random string, if you take, it's supposed to have a bunch of zeros and a bunch of ones. So it will never be self-dissimilar because it's supposed to hold for every substring, right? So you can't even have like 0, 0, 0, 0. Like there is no 4 zeros that should be there consecutively. No pattern at all, so that there is an align. So the only way we know they exist is through Lowash local lemma. Very magical, but yeah. And then yeah, the point is to analyze these things. You get like very weird expressions, and you need to somehow guess a lot of estimates and prove these. So yeah, the point you get is there's a 1/8 isometric thing. If you give me several more years, I think it can be made 1/7 with just running the same code. And I think the true answer is probably 1/4 or 1/5. And I don't think we can get 1/4 with this framework, but 1/5 maybe with enough atoms in the universe, yeah, should be doable. But let's talk about the other side of things, the from well, as I said, more atoms. Okay, now I want to talk about the impossibility thing, that you can't get half. In fact, you can't even get 15/32, which is less than half. And to prove this result, the first thing that we prove is step 1, that any isometric embedding must look like padding. This is a very strong statement. So what it's saying is that there is no other non-trivial thing. You can't just combine few of the input bits and write a bit. None of these work. It must look like padding. So it must be like you take some fixed string and interleave it with the input string. It's a very strong result. Yeah, I won't prove this, but you can show that this is necessary for isometric. It's not necessary for one embedding where you allow for a constant scalar multiplication. But then if you're allowing for a constant scalar multiplication, since these are discrete metrics, the rate already goes down by the scalar factor. So you already pay because of that. Okay. And once you have this, you can already see that why this is surprising, right? Because somehow intuitively, these things that you have should be error correcting codes. And in the Hamming metric, you have error correcting codes approaching rate close to half and so on. So this sort of provides a separation. In fact, you have error. You don't even need a constant distance. You just need some distance. So these exist even in edit metric. So what this says is these isometric embeddings are a stronger object than just error correcting codes even in edit metric. Okay, once we have the step 1, that we showed that it's just like a padding. Step 2 is then, okay, let's assume that there's a very high rate interleaved embedding, and we'll show it's not isometric. And the way to do it is using the probabilistic method. We define a distribution over all pairs x and y with some alignment, which is just defined by a random shift. And we only condition it on those pairs x and y whose Hamming distance is n. So you just have basically 2 to the n-1 pairs. So you look at every pair of opposite bit strings, and on them you take a random shift, and you show that in expectation, the edit distance is less than n if the rate is high enough. Did we die again? There is one more slide. I think it's fine. You can thank them later. Okay.
I think you want to record the.
Yeah, it's being implemented.
You will have to type it. While he's taking that thing, say a little bit about how do you do step 1.
How do you do step 1? So, okay, let's try to think of this intuitively, right? So suppose.
Do a lower bound.
Yeah. So suppose it's not. What we want to say is that the ith bit of x, let's say it influences 2 bits of the embedding, right? And then you want to sort of construct these xy pairs such that I get a contradiction. I loop back and I get something which is not happening. Do you see this? So I have, let's say I have a fixed embedding where the ith bit of the input goes to some I prime bit of the output and then some other bit of the output and so on. And maybe there are 2 input bits which contribute to what an output bit is. Okay, so we have all these things. Then what we will say is that, okay, fix some x, okay, and then I will change it on that specific coordinate. So x and x plus ei. And then I know it's supposed to affect these things. And then I'll change it such that I get a contradiction just because the edit metrics will, yeah. So each one has to be like independent. That's basically what it shows. And if it's going to be independent, there's no reason to duplicate. So it's just some permutation of this written. Okay, anyway, so coming back to this, you look at all possible pairs which are at distance n, and for each of them, you just take a random shift. And then we show that in expectation, the edit distance is less than n. That means that there is some shift. I don't know what, which one. It depends on how we define the embedding, but there is some shift whose cost gives me less than the Hamming distance, so it's not isometric. Yeah, it's because of the analysis when we do. Sorry? Yeah. So the 1/32 is just some constant we can choose so that the expectation analysis goes through. Yeah. It's easier to see for rate 2/3 because then you can think you will always have three things. So you'll have three input bits that are written together, and you can always just construct three input bits where it's better to do edit than having. So it's like, what is the shortest number of bits I need so that I gain something with edit distance? You don't gain for one, you don't gain for two, but three you start to gain. So 2/3 is, you can show more than that is not possible. It requires work to show a bit for half.
What about other metrics? The main.
Which metric?
I don't know any other metric.
You mean exact? What Kindle tau, Lang?